Good morning. As Laura said, I'm Craig Olson. I don't have a tie on. I don't usually wear one if I can get away with it, along with my colleague Richie Youngworth. And today we're going to give a very brief overview of our short course that we teach twice a year at SPIE, Practical Optical System Design. So both of us have been doing optical system design and engineering for a long time now. I forget how long. I think Laura mentioned it, but it's long enough that we've made enough mistakes. It was worth starting to write them down and tell other people how not to repeat them. One of the things I want to point out is the word practical here is really the relevant word in the course title. And what that means is we're not going to give a lot of derivation and math behind some of the topics that we're talking about, but it is going to provide a lot of context and experience with some basic level equations. And if you think about what engineering is, providing context around design equations is really what engineering is. So with that, I'll say any of the mistakes within this presentation are definitely Richie's and not mine. He's going to tell you the same thing, so neither of us have any problem throwing the other one under the bus, but that's what we're here for. Could you flip to the next one, please, Richie?
I don't know after that.
See, I told you it'd be his fault.
I don't know if I can. Oh, there we go. All right.
So just as some context, this is listed as an intermediate level course. So it does provide presume some prior knowledge of or exposure to kind of optics or physics 101 type stuff, geometrical optics. But we do cover a little bit of the basics. And as I like to say, the idea is you should have at least slept through the right classes, as I did with all this geometric stuff. So it is good to have a little bit of background coming into it, but you don't necessarily need to. What we're really trying to do is to expose anyone who might work with an optical designer or engineer some technical exposure to the stuff that kind of goes on under the hood. So you have a working knowledge at a pretty high level across the board of optical engineering, working on different projects. Next, please. This course has been actually going on a long time. I think it's SC3, which means, if I'm correct, it's the third course that was ever really offered by SPIE, going all the way back to 1978, when I was young enough to see Star Wars in the movie theater. And it was founded by Robert Fisher, and he was really a pillar of the optical engineering community. And he loved teaching and he loved optical engineering, and he was teaching this course right up until the day he was not able to do it anymore. So that's kind of the history of where we're coming from. So with that, I think, Richie, I'll hand it off to you.
Muting and Zoom and fun. So there are some learning outcomes we have for the course. One of the big ones is so you understand how to write a specification. That's obviously really important from a practical perspective, because the better specifications you write, the more problems you're going to avoid. Or if somebody wants to add something into a specification, you'll tie it to the design better. We also talk about some fundamental physics and engineering related to optical design, give a basis for modeling optical systems using computer-aided methods. Now, we don't specifically focus on any particular code. We try to keep things out of the code, but the information we talk about works well with computer-aided types of methods. Talk about analyzing and organizing systems for many different factors, including environmental. Talk about design for manufacturer alignment and testing. And the big message there is always to consider those factors as early as you can. We also talk about multiple key aspects of optical engineering to take things from concept to production. Not at a level, say, that a full-blown tolerancing class would discuss, or something on drawings, for example, but something that the optical engineering framework and fundamentals are in place. So we thought that we would at least give a quick review of the course outline. So these are good ones if you're going to screenshot a slide or go back and review it in the video. We give the background and overview is just a little bit of what we gave today, but then we go into some basics, sort of number 2 basic optics, some first order optics, monochromatic aberrations and chromatic aberrations. Leading in then after that fundamental work is things that get even a little bit more specific to optical design, image quality criteria, writing specifications, and just a general optical design process. And anybody who's done this kind of work optical design and engineering, there is not one formula. Even specific optical engineers and designers may take different approaches on different jobs. Then we talk about some configurations, and this is first order configurations and just an idea of what types of configurations have traditionally been used to solve problems. And this is an always evolving type of topic. Then we go to some materials selection, glass selection, and color correction. We also talk about advanced surface types, and what we mean by that are non-spheres, but it also includes diffractives and gradient index, at least enough to get you started. And then some of the history of this class is when we took it over from Bob Fisher, we actually sat down with some other course instructors from SPIE and just tried to make sure we were covering some topics that maybe weren't covered as much in other courses on optical engineering. So Gaussian beam optics and infrared systems. We do just a little bit on ultraviolet. They're so highly specialized that if you're going to get into that, you're likely to be working with experts to begin with. Some use of off-the-shelf optics as well. So those are kind of general topics that aren't covered in a lot of other courses as much on these sorts in optical engineering. Then we talk about optomechanics and environmental, at least from an optical engineering perspective, not something to the extent that an optomechanical engineer or a mechanical engineer doing optical systems would necessarily do. A little bit of intro to stray light and coatings, design for manufacturing and tests, and then computer-aided optical design. We have started building up some selected references. Of course, at this point, the literature is quite extensive in this area. Okay, so now I'm going to hand it back over to my co-presenter.
So, as I mentioned, another name for practical design is also engineering, although that sounds like it's words that could spur a bar fight. But one of the differences, I like to differentiate design versus engineering, and we do a bit of both in this course, as you have to. A lens design on the left is really where you kind of worry about first order layout, power distribution, focal lengths, what's the f number I need, what kind of aberrations am I likely to have. Other things you can determine, you can optimize deterministically with rays. So that's something that would come out of a lens design code. On the right, we kind of have what you really want to end up with in the real world, which is a real functioning lens that, here's a good example of where we took a starting point design and ended up converting it into real glass and metal. So you have to worry about things like stray light, tolerancing and build, not only from the component perspective, what are the tolerances on the components, but what is the allowable motion that I can have when I'm putting these things together? What kinds of focus am I going to have? Which cell am I going to move to focus? What's practical? How am I going to move those cells? And then these things need to work over temperature and vibration, because at the end of the day, you're going to hand it to somebody that has no idea what that is. They're going to bolt it in, scrunk it down as tight as they can, and ask you why it doesn't work. So, like I said, it's starting with the left, you have glass. You have to remember that we have to wrap metal around these pieces of glass, and not the good kind of metal like 80s hair bands like Kiss or Iron Maiden. We actually have to wrap aluminum or titanium around them and squirt glue in there, and they need to hold. So bridging this gap between a good solid optical design, which takes some creativity, like the kind, Bob Ross painting his happy trees, you need some creative there, but you also need the engineering aspect of bringing all these things together. And that's a good team will iterate there between those two, as it's not just a design something, throw it over the wall. And what we really talk about with that laundry list of things is what are all the aspects you need to consider when you're building something like that. Another way I like to summarize it is, on the left, designers use image circles because everything's rotationally symmetric and easy. On the right, we have square focal planes and rails, so you're trying to put a square peg in a round hole. That's another good way of looking at this slide. Next slide. Just to cover a bit about light, there's three ways of describing light, which you might remember from physics or optics if you had it. In geometrical optics, which is really, I won't say the simplest form, but it's the least, often considered the least mathematically rigorous, even though that's not true. We deal only with rays. that really represents an ideal representation of how light travels through lenses or reflects off mirrors. And it's very useful for not only just lens design, but also all of optical system design, even illumination. And really, you only need 3 pieces of information to trace a ray. You need to keep track of the intensity, you need to keep track of the optical path length or the phase, and if you really want to get fancy, you keep track of the polarization. So from that perspective, that's why rays are so useful. It's very computationally efficient and very fast. Stepping up one level of complexity. Sorry, I'm muted. Am I back? Was I muted?
Back. Yep.
Okay, I'm not sure what happened. The wave nature of light, which is really diffraction. So you have Fresnel or Fraunhofer diffraction, and where you think about a wave front of light coming in diffracting from an aperture, and you have things to consider there. That's also dealt with a little bit in optical system design. The third way of dealing with light is quantum optics, where light is actually considered these little bullets of packets of energy called photons. And that really is a useful way of dealing with how light interacts with matter. So we really don't talk much about quantum optics in optical system design and engineering. On the next, please. What we really focus on in the course and in most of optical design is geometrical optics dealing with rays, and physical optics where you need to worry about wavefronts and diffraction and propagation. Really, the only time you deal with quantum optics is if you're doing the radiometry of engineering, where you need to worry about the focal plane as little quantum well detectors. But basically, most optical design codes, like Richie alluded to earlier, are really set up to deal with the first 2. And you can get an awful long way with those 2 methods of dealing with light.
Okay, so that's, if you haven't gone through all of that physics, that's why we try to give at least a little bit of an introduction. And it's kind of expected for new optical engineers who haven't necessarily done a lot of that it takes a little bit of time to get used to some of the physics, especially the geometrical optics. But one of the factors in geometrical optics is that the way optical systems work at a fundamental level is with what we call first order properties and then aberrations. And the real fancy math involves Taylor expansions and all sorts of things like that. Design codes certainly help you out with this. We try to give people a running start in the class. So we cover different cases. So for example, spherical aberration. Every single one of the lenses that you see below has the same first order properties. In other words, they are all the same focal length and they are all f2 for the f number, which for a system at infinity is the width of the beam divided by, the focal length divided by the width of the beam, the entrance pupil radius actually. So they're all f2. So this is a fast system. This is one that we know we probably can't correct very much. Well, we know we can't correct it as well as we might like with just one lens. And you can see that here. Depending on how this lens is bent, you can see just with your eye how drastically different the focus is, how different the disk of confusion would be in this. So the question is, which one would be the best or most practical? And I can tell you already, most problems that you deal with, you won't be able to tell by your eye. You have to trace rays and look at a design code. But one of the key things you can look at is the spherical aberration, which is the change in the power across the beam or across the aperture. So this is just an example of one of the factors when you look at, when you either design or for our purposes, we look at the system and we're considering what's practical. We try to assess aberrations at times to make sure we're making the most manufacturable system. One other comment probably worth making here is if you can use a singlet, obviously you'd want to use a singlet, but sometimes you might need more lenses for performance or some other types of reasons. Usually it's performance. We also cover color effects, which is chromatic aberration. So here's just an example of the dispersion you would get with light focusing down through a lens, but this case is not like what you would have with just a single glass. In this case, we've actually intentionally corrected it to at least get the red and the blue focused at the same location. So that's residual aberration, color aberration would be what's called secondary color, because the primary axial color between the blue and the red has been fixed. So you would get those two in focus. Of course, you'd have to figure out where to put a focal plane in this type of system. How is this done? That's part of what we discuss in the class. There's some theory behind it, but essentially you make the lenses from different materials with different dispersion. One is positive in power, one is negative, and that allows us to correct this. I can't remember if this was me or you. I think it's still me for this one. I'll go ahead and do it. Image quality is never perfect. We have these geometrical aberrations that we've discussed. This shows spherical with this singlet, and this is entirely predictable and mathematical. The other thing that affects image quality at the most basic level is you have diffraction because you're truncating a wave. And the way diffraction works in a lens with a circular aperture is if you assume all the diffraction is happening at the exit, what we call the exit pupil, which is the image of the stop after going through all the optics, then you would end up with the Airy pattern in that case, if it is perfectly diffraction limited. There are, of course, cases where you have some geometrical aberrations mixed with diffraction effects. And in those cases, you have to start determining what is really the driving factor. We cover a lot more aberrations and a lot more image degrading effects in the class. And our purpose is not to make people lens designers in this, although you can do some lens design with what we show. The purpose is to help you as an optical engineer understand the systems. Okay, back to my co-presenter.
Yeah, so as Richie alluded to, well, I'll just comment, if you can interpret a ray fan, it's a very powerful thing, because if you're not a designer and you're sitting in a meeting and you say, can you pull up the ray fan, people will instantly think, oh no, he knows or she knows what they're talking about. Whereas in reality, you have to be a wee bit cracked in the head to interpret one, but it is a very useful skill. As Richie alluded to earlier, covering specifications, this is really an important thing. If you learn nothing else, you need to learn all the things that you need to specify for an optical system. It's not just, I have a focal plane this big and I need a field this big, I need an image. There's a whole slew of other things that are important. Those are the three most relevant topics that are important. The focal length, the aperture diameter, and the F number are all intrinsically related. And those are very important to specify, but you also need to worry about what the wavelength are, what's the mechanical, environmental, how much light do I need? Am I imaging in the dark? Is it infrared? Is it full daylight? Distortion is always one that's forgotten until the very end, so it's important to consider that. And just generally, what kind of imaging performance do I need? Am I Hubble Space Telescope quality, or can I get away with like a photographic quality lens? So we talk a lot about specifications and what's important to cover when you're dealing with a system. And along those lines, really, understanding, we explore a lot of different design forms. What's a design form? Well, it's either a refractive lens, or which is glass that focuses, or a reflective system, which is mirrors that focus. How you lay out and distribute the optical power in those elements is important. And here's kind of a canonical map that we adapted from a classic of Warren Smith's modern optical design that linked the two fundamental parameters of an imaging lens, numerical aperture, which is equivalent to F number, and field of view, angular field of view in this case. So, and you can see what happens is those are the two things. If you know those things right off the bat, I need this F number lens, which tells me the cone of light coming in, which tells me how sensitive it is, and what field of view I need to cover. I can sort of get a head start on what kind of lens form I'm going to need. And you can see there's very wide variety here between the types of lenses. On the bottom left, you have a singlet, which covers a very high F number and a very low field of view. But if you need a very, very wide field of view, like over 90 degrees and a very low F number, then you need a retrofocal design. So you wouldn't even consider starting with a singlet or even a telephoto type design. So learning to sort of jump your way over these two fundamental parameters, numerical aperture and field of view, is a pretty good skill. Pretty good skill to have under your belt. There's a similar chart for reflective systems that we also cover, but not here. One of the things that we have added into the system, which is more and more important, is laser optics. So we do cover a little bit about laser optics and laser and Gaussian beams. Beams are a little bit different than rays in terms of how they interact with powered surfaces, as well as how you use them in the optical design codes, and usually you need some physical optics to get the best results. So laser light's different from regular incoherent light in a few different ways. It has speckle, which you can see down there at the bottom right. That's kind of what you'll see with your eye if you shoot a laser pointer at the wall. You have coherence. Laser light's usually coherent. Unlike this talk, of course, but what that means is the phase of the wavefront is deterministic, both in space and possibly also in time. So you get a very good predictability or deterministic prediction of the phase, unlike incoherent light. And finally, laser light's very directional. You can talk about it in terms of beam optics. And then we go over a fair bit about some laser applications. For example, you could have a simple system like a cube retroreflector, which those are a little bit more complicated than you might think. And those are used both as lab instruments, and you also might see them on a satellite orbiting way up in low Earth or mid mid-Earth orbit, where you need to shoot a laser at it and get a solid return. I might have a beam shaper down on the bottom right where I need to take a Gaussian and turn it into a top hat, or I might want to expand my beam or reduce it. I might need to scan the beam or steer it or raster it in a pattern, or I might have a more complicated system like a data storage system, like you might see on a DVD or a Blu-ray. I mean, I don't know who uses DVDs anymore. I went right from VHS to HD streaming, so I don't. But no, those are all sorts of things that need to consider beam optics. We talk about a little bit of the details about imaging with beam optics. So with that, we cover an awful lot of subjects in the course. This is one of my favorite pictures since it kind of links all the stuff from an entire lens assembly that doesn't show up in the ray design. If you remember that first slide, we have just the ray design, which is those little rusty pieces of glass. I'm not sure how glass rusts, but these did. And then you have all this complex optomechanical structure around it to hold all the tolerances in place. I really love this picture. I've always wanted to do this, but I've never been able to convince our management to let me saw one of our $1 million systems in half. So again, as Richie mentioned earlier, we talk about glasses, A-spheres, infrared, ultraviolet, optomechanics, testing and fabrication, and a lot more. So with that, unless you want to add anything, Richie, I think we can open the floor.
I'm just going to make a comment about this picture. So this picture came from, there's a camera show, was going every year, usually somewhere in the Tokyo area. I went to one in Yokohama, and I found this picture on there because it's pretty common. Some of the camera companies from Japan would actually cut lenses in half like this, just as part of the show. It was sort of this everything you love about imaging kind of show. So that's where this picture actually came from. Okay.
Thanks, Richie and Craig, for that excellent presentation. As a reminder, folks, if you do have any questions, please put them in the Q&A. I don't see any in there quite yet, but we do have some good prompt questions here. Richie and Craig, when do I care about geometrical effects, and when do I care about diffraction in a design?
So I'll go ahead and take this one. It depends on the system. Usually in a design code, there's a threshold where it's going to switch between the two. So if I'm ever unsure, I look at both. And when you look at both of them, and this is because some calculations are actually done with geometrical and some are done with diffraction. Some include both properties. So what I try to do is just do enough analysis that I'm sure I've got the worst case covered in terms of what would happen. So if I think diffraction is going to really be driving it, I make sure I look at the diffraction properties because the geometrical properties might be perfect. So it's just a matter of being careful, doing enough analysis, and if you're unsure, talking to other colleagues.
Yep. Practically speaking, it's when the amount of sampling you need to get a poorly corrected image from a diffraction perspective makes the computation time increase above where you need to trace enough rays from the geometric part to get a solid answer. That's sometimes that's what it boils down to, but yeah, this, the spot is the convolution of the geometric spot with the diffraction spot. So it really is a continuum.
Great, thank you. I have another question here. What types of additional factors would I need to consider when specifying an optical system?
Well, yeah, it's a good question. We design a lot of stuff here, and we do an awful lot of we'll do build to print, and we'll also specify a lot of assemblies. And usually it comes down to the one thing, if you're specifying a system and you just have focal length, F number, and size, weight, the size and weight of the system you need. A lot of times it's the nuances of thing like stray light, where most vendors that are building a system won't necessarily be thinking about stray light or ghost reflections or things like that. It really depends on kind of who's designed it. If you're handing somebody a design that you've done, then there's a bit of a different onus on what's to be expected.
Yeah, sometimes with stray light, you might need to put some extra blocking vanes or something in it. You might want to process the inside of the barrel differently, put threads in, bead blast, sandblast it. There's anodizing, but that doesn't work in IR. But there's other things too. And in a good optical specification, you would certainly want to include environmental factors for temperature and such, because the optical engineer may need to do some analysis around that factor. There may even be things that, let's say the system operates in the visible, but this was more common in film, but you would get washout if there was some IR. You may want that in your specs, so you're sure to include a filter of some sort in the system. There's just a lot of factors that can come into play when you're specifying it beyond just what the optics are doing. I had a recent problem where there was some students, they were looking at an arthroscope, and that type of application has a rigid rod, and they wanted to do a specific thing with it, which I can't really talk about, but it had extreme packaging constraints. You can't make it bigger because you're going to stick it into somebody. And certain systems have those kinds of constraints. If you're sending stuff into space, there's going to be contamination effects and other things that you have to really consider very carefully. And many of them go into the mechanical engineers world as well, but they really need to be in the optical engineering domain. Perhaps the last one really worth mentioning is things like post-processing for computing images and such. If you have certain corrections that can be made in post-processing or with image processing types of methodology, then you want to include those as well. And you can even see how that's advanced if you look at mobile phone cameras now versus where they were 10, 12 years ago, how much of a difference that's made. The lenses are certainly better, the sensors are better, but there's all of those factors too. And we could probably go on and on and on about what illumination you're using and application oriented stuff. So there's a lot of extra factors that we go on.
We do for a full day.
Yes, we do.
Thanks, Richie and Craig, for that thorough response. I do have another question here for you. Is there a map or chart for field of view and speed for reflective systems?
Yes, there is an equivalent chart showing like TMA, 3-mirror anastigmats, and Cassegrains, and Ritchie-Chrétiens, and Schwarzschilds. We just didn't include it in this summary. It's in the short course, and it's also in the SPIE Field Guide to Lens Design. Not that I'm plugging things, but if you have access to this, we did cover that in there, and those are derived from a classic diagram in Warren Smith's Modern Optical Modern Optical Design book, which is also relevant. Yep. That was not a shameless plug. That was a reference to a source of information.
Absolutely.
Actually, this is a shameless plug. This just came out. All right, I'm done.
Nice tag team there.
Yeah, thanks.
Okay, so another question. How or why is this different from a lens design course?
So a lens design course, you talk about a great number of systems. And for example, that chart, you would talk about many of those kinds of systems, why certain things are done to make corrections. And you would talk a lot about how the aberrations are corrected, because that's what lens designers do. They spend a lot of time making sure that they meet all the requirements and correct the aberrations. And there's a maxim in lens design that you don't get partial credit in lens design. So if you get most of it corrected, it's still not going to work. So that process of designing lenses or understanding how they work at that level is a much, much deeper dive than what we do here. What we do here is give somebody enough information so that if they're the optical engineer, they understand how it works. And that is part of what you need to do when you're talking to the fabricators or working with reviews and other things that the optical engineering requires, and all the analysis. I don't know if I've got enough, Craig. Maybe that's good.
No, I think, yeah, it's like I said, anyone that can interpret a ray fan in detail is somewhat cracked in the head, but it is a valuable skill, even if you're not a designer, to be able to interpret. You can determine sensitivities and all sorts of things from knowing a little bit about the design process without going full bore into all the details.
In the old era, what I would do is I could talk to an optical engineer, but if I was dealing with a lens designer, I'd first have to figure out what was wrong with them because of their just unbelievable ability to dig in at the level of detail that it takes. Obviously, I'm somewhat kidding. And I think those days are a little bit gone now, but it used to be that lens designers are a really special breed because of the depth of knowledge and just being able to see things with the design and know why it's being corrected. And to you, when you're starting, you might just look at it and go, oh, there's just a few rays bending there, and they see something different than you do. It's very interesting, but much deeper.
Square peg in a round hole.
Thanks, Richie and Craig. It's really interesting to hear these responses from my perspective. We've been scheduling your course for many years, but I've never actually been able to sit in on your course. So this is kind of a nice little way for me to sit in, like I'm the principal or something of the school, and I get to sit in the back of the classroom. Okay, so we have another question here. Why are only geometric and physical optics relevant and not quantum optics? Seems like a good question these days. Quantum is on the lips of many these days.
It is very much, and it's a good question. We generally, so the course focuses on, generally speaking, imaging optics. We don't do illumination. We don't do photon detectors. We're not doing anything super exotic like metamaterials or meta lenses. So it's really intended to focus on systems that you can design, optimize, and engineer with some of the commercial ray trace codes. Or if you're completely insane, you can write your own ray trace code. But the point is that the math and the utility for the systems that we're covering in this course are really very much completely covered by geometric and physical optics. Quantum optics does come into play. And in my world, I have to, so you want to know, how do you figure out what the F number of a system is? Well, you run through the radiometry of the system, and you'll have a CCD or a CMOS camera. And then you have to do some quantum optics calculations to sort of fill how many photoelectrons do I need per unit integration time. That's more or less the limit of where I engage with quantum optics, unless I'm going more into detail about focal plane sensitivity, which is kind of ironic. My whole PhD thesis was on semiconductor lasers, so it was nothing but quantum optics. So that's my take on it.
I agree with everything, of course, but there's one additional thing that I like to point out. The speed of light in vacuum is, we call it C, right? 3 × 10⁸ meters per second. But what's the speed of light inside of a material? And the answer is the same. The reason why there's an apparent slowdown is a quantum effect. Energy is absorbed and then spontaneously re-emitted, and you have this aggregate effect over many, many photons of the wave slowing down. But the actual quantum is quite a bit different. I don't care when I'm looking at it from an optical engineering perspective. The wave approximation, or even at a ray, the approximation of the change in the speed, which changes the path length of the rays, is more than enough for us to do the job that we're doing.
Great, thank you both. Looks like we have one other question here. And again, I'd like to encourage folks in the audience, if you'd like to ask a question, this is a great opportunity to ask these two experts. If you prefer not to ask your question directly, feel free to write it in the Q&A anonymously, and I can read that out for you. We do have one more question here. What types of optical materials does the course consider?
There's a whole slew of discussion on standard optical glass, shot, O'Hara, things like that. So we spend a great deal of time going over glass maps, what the specific nature of visible glass. There's also quite a bit of information on infrared materials, silicon, germanium, chalcogenides, things of that sort. So we do actually spend a fair amount of time talking about the materials. I think it's probably close to 20%, maybe 15 to 20% of the class.
Yeah, and the IR materials and a lot of those that Craig mentioned, he's updated those pretty recently.
Yep, I've got that session's updated, and I will plug Alan Simmons and another SPIE field guide for infrared optical materials was just published, which is actually a co-parallel update of a lot of the stuff that we've updated. So the infrared stuff's up to date, very much so. As far as UV materials or laser glass, we don't spend a lot of time with the UV materials. I think there's only two.
Well, there's not many. Yeah, there's not many UV materials, and the transmission becomes important, and they're all expensive as heck and specialized. So we don't tend to spend as much time there because you're going to be dealing with a material supplier regardless.
Yep. But other than that, I think there's a fairly comprehensive overview of traditional optical glass like you get from SCHOTT, O'Hara, or Hoya, as well as the infrared materials.
We don't talk about substrates, or we don't talk about cladding for reflective systems or things like that too much. So either, because that's kind of getting into the mechanics quite heavily.
Thanks, Richie and Craig. It looks like we're getting some questions in from our audience here. If you would like to unmute your mic when I call out your name, please feel free to ask your question directly to the instructors. I have a question here from Kieran, I believe, K-I-R-A-N. My apologies if I mispronounced your name. If you would like to unmute your mic.
Hello.
Hi.
Yeah, hi. I wanted to ask that whether production of like surface plasmon we are considering while designing an optical instrument, like how much extent we need to consider the production of surface plasmon in case of lasers.
So are you designing a system to collect a readout from a surface plasmon experiment?
No, like I wanted to construct an instrument which can be useful for both the surface plasmon experiment and the normal spectroscopy experiments.
So that's probably where that's a good example of where you need more information about exactly what sorts of signal you're trying to collect, what levels of sensitivity, and what size field of view, what size of. One of my colleagues in grad school was doing experiments on surface plasmon, so he was always trying to get enough signal through a spectrometer to do the Q measurement on the resonance. But again, that's actually a pretty good example of where you need to sort of sit down and think through what it is you're trying to do. What are the commonalities between the two things? Do I need, how much light do I have? Am I looking at internal excitance, or am I exciting externally? Am I collecting edge on? Am I collecting surface on? What's the geometry of the collection? If I think about designing instrumentation optics, so without knowing too much more about the details, I think it's a hard one to get any traction on.
I think from the correction of aberrations and that sort of perspective, it's not as key there unless there's some sort of a radiometry effect that's also taking in, or a scattering kind of effect or something like that that'll wash an image out.
But that's, like I said, if you know the field of view that you need, like how big a thing am I trying to collect a signal from, and I know how big the numerical aperture or how low the F number needs to be, which you get out of a sensitivity and radiometry, then you kind of look on that landscape map for reflective or refractive systems and say, okay, well, here's kind of the starting point that I would need to do. And then depending on the quality that you need, exactly, that's kind of where you take it from there. I hope that kind of touched on what your question was getting at.
Yeah, thank you. Thank you.
Great, thanks for that question. We have another one here from Brett Rosenberg. Brett, if you would like to unmute your mic, you're welcome to speak with the instructors directly.
Hi, thanks, Laura. I work with a sulfur polymer that has a broad band of IR transmission. I'm curious if you guys have come across something like that.
No, are you selling it?
No, it's very embryonic. I work with chemists that synthesized it. We're working on a patent and got a couple positives on it in terms of Air Force Research Lab looking at it, seeing a couple promising things, but we're looking for complete optical characterization of the material so we can understand where it can play.
Yeah, I mean, so from my perspective, new infrared optical materials are, I'll nerd out here and say, are extremely exciting to me. There's not a lot, there's chalcogenides, there's IR glasses, there's the new NRL series of glasses that are multiple chalcogenides. There's not too many plastics or polymers that are out there. I've worked in polymer optics before, and there's even a similar discrete selection in polymers like there are in infrared. So yeah, depending on the transmission and the mechanical properties, I think there could be a lot of interest in something like that. Are you able to say which AFRL group that you're engaged with?
Yes, in Dayton, they actually provided us with a letter of support to try to go after some SIBRs and things of that nature. And all of that, yeah, I was okay to share their feedback. But it's, like I said, it's very embryonic. We don't have those questions answered about the mechanical or optical properties that really need to be done. So we're looking to accomplish that.
Well, I'll give you a shortcut. And I'm not plugging this, but I was just looking through it last night, the SPIE field guide for infrared materials. It has a good sort of laundry list of, if you can answer.
I just bought that.
Okay, so yeah, they've got it's like trading cards. They've got trading cards in the back. Like, oh, I'll trade you 1 germanium for 2 silicons, but that's kind of the laundry list that we look at. So
also how it's going to be processed is going to be absolutely essential.
History of the materials is very critical.
Very, very important of how you can get it to the level of quality that you would want or need for that type of an application is another huge factor beyond just the material characterization itself. I'll give a couple other little pieces of info on that. So in the standards world, there is a task force that is trying to characterize IR materials in general, because this has been an underdone subject. And there was some people at NIST that were working on it. So that group is the OEOSC. And it's, I think it's just oeosc.org. And there's a task force, I think it's Task Force 6, that's looking at that. So you should at least dip your toe into that to at least see where that stands. Now, of course, standards are going to follow way beyond where you would be in this kind of embryonic stage. However, it's where you're going to want to get to where it's robust enough to be like the other materials.
So I'd be happy to follow up. I know some of the folks in Materials Directorate. So.
Well, that's awesome information, guys. I appreciate that. Yeah.
Great, thank you so much. Thank you for your question. It looks like, unless there's any others who'd like to squeeze in a question here at the end, or Richie or Craig, if there's anything else that you'd like to add in the remaining few minutes here.
So I have to agree with Craig's assessment. All the mistakes in the presentation were mine. All the errors in the answers we gave were his, though.
Yep. Nice. Sound of speed bump. No, these things are great. I love doing short courses because there's one way to expose one's ignorance. It's to try to teach something. So after, I don't know how many years, I'm certainly still exposing it, but it's fun to hear what all the new problems are from people.